Now what else we'll do here let us see this impedance of a transmission line. The impedance of a transmission line means what? As we have seen the expression for the voltage and current, we have seen. Next we'll see about the impedance of a transmission line. Impedance of a transmission line. So consider this is my transmission line here. This is my transmission line, so I can call this as x is equal to L. I will call this as x is equal to 0 now. Now here these are the load terminals. These are the terminals of a load, isn't it? So this is this impedance. This impedance we'll call it as a ZL. ZL is the load impedance, and which is given as what I can say here, VL by IL. I can say now load impedance is equal to load voltage by load current is a load impedance. And of course this transmission line will have some characteristic impedance. I can say Z0. Characteristic impedance is Z0. As we have seen the expression for voltage and current, and what is the expression for voltage? We have seen V of x, that is in terms of cos and sine. We have seen the expressions. Now tell me the expressions what we have seen, that is VL into what? Cos h gamma x plus IL Z0 into sine h gamma x. Next I of x, which is equal to IL into cos h gamma x plus what? VL by Z0 into sine h gamma x, isn't it? Yes. IS is equal to correct only na? Right. So these are the expression for voltage and current we have seen now, isn't it? What are the V of x, I of x? What these are? What are the V of x, I of x will give? That is the voltage and current at any point inside the transmission line, isn't it? By using this V of x and I of x, we can get what we can get, the voltage and current at any point inside the transmission line. So this V of x will give us a voltage at any point inside the transmission line or not. So what I can say here, let us consider from here, and what the x is the distance measured from where to where? Load to source. X the distance from where to where? Load to source. So if I want the voltage at some random location, I can simply replace the value of x value and x the distance measured from where to where? Load to source. I can replace, then correspondingly I can get the voltage at that location and current at that location we can get now. Now let us consider, we have taken some point here. Let us say this point. I have taken this point here. Now let us say this is at a distance of x from the load. X distance, some distance, random x distance from the load. At that location, I can call this as a voltage. I can call it as what now? V of x. At that location, voltage, I can call it as what? V of x, I can say. At the same location, I can find the current. We can find that current. I can call it as what now here? I of x, I can say. At the same location, I can call the current as what? I of x. V of x is the voltage at this location. I of x is the current at that location now. Now, if I take the ratio between these two, then what I will get? If I have taken the ratio between these two, then I will get impedance now. Impedance where? At the corresponding point. I will get the impedance where at the corresponding point, then I can call it as what I can say impedance, that I can say z of x, I can say, isn't it? Z of x. What is z of x? Is the impedance at the corresponding location. Z of x, which is given as what? V of x by I of x. That is the voltage at the corresponding location to current at the corresponding location will gives what? Impedance at the corresponding location. Isn't it? Right. So let us the remaining analysis simple normal analysis only. Simply so to get the z of x, and we need to take the ratio between these two. We just have to take the ratio between these two now here. So let us take the ratio between these two here. That is my z of x, which is given as what now? Yes, v of x. V of x. What is the v of x we have seen? That is VL into cos h gamma x plus IL z naught into sin h gamma x by IL cos h gamma x plus VL by z naught into sin h gamma x, isn't it? Now you can see this thing VL by IL is equal to ZL from this VL. So I can write this VL, which I can write it as simply what I can write IL into ZL, I can say now. VL is equal to IL into ZL, I can write. So this thing, so this VL I can replace it as what now here? IL into ZL cos h gamma x plus IL z naught into sin h gamma x by IL cos h gamma x plus VL, that is IL ZL by z naught into sin h gamma x, isn't it? So now this IL will get cancelled. IL will get cancelled, and denominator we have z naught. Take the LCM with z naught, and the z naught will come to numerator, I can say. So finally z naught is equal to what I will write now here, ZL into cos h gamma x plus z naught into sin h gamma x, z naught into cos h gamma x plus ZL into sin h gamma x, isn't it? This is my z of x. This is my z of x now here. So this is z of x. Now if I divide with a cos, if I with cos, then here what I will get now here? This is ZL. This is ZL plus what? Z naught into what I can say this as a tan h gamma x by z naught plus ZL into tan h gamma x, isn't it? This is my z of x, I can say. This is my z of x, I can say. Isn't it, Akshay? What is the z of x is the? What is the z of x? This is the impedance at any point inside the transmission line. Isn't it? Impedance at any point inside the transmission line. Let us consider I want the impedance at the load. What I should do? I want the impedance at the load. For that, what I should do here? Yes, at the load, I want the impedance now here. Tell me what I should do. I should replace x value equal to 0. Now see this thing, what tan hx, tan h 0 means 0 now. So then what I will get now, z of x now here, which is equal to simply zl, isn't it? We will get that as what? Zl, not zl, that is the impedance of the load we have considered, isn't it, Akshay? Right, so that like this. So here, by using this relation, we can get the impedance at any point inside the transmission line. By using this relation, we can get the impedance at any point inside the transmission line. So that is z of x is equal to what? Zl. Z of x is equal to Zl. So this is, by using this thing, we can get the impedance at any point inside the transmission line. And try to remember this relation, which is a very, very important relations. Now let us do a little more analysis about this impedances now here. Yes, as we have seen the z of x expression, which is equal to what? Z naught into ZL plus Z naught tan h gamma x by Z naught plus ZL tan h gamma x. Now you can see this thing here. Now consider my transmission line at this is, the load is short circuited. For in case of a short circuited, the short circuit line means SC line means what now? The short circuited transmission line means what happens now here? This is my transmission line and here this load is shorted. That means what now here? Load impedance is how much it is at 0 and this characteristic impedance is how much? Z naught now. I want to get the input impedance of this thing here. Yes, the impedance at this location. So the impedance of the short circuit transmission line, so I'm calling this as a ZSC, I can say. Impedance of a short circuit transmission line, I can call it as ZSC. Tell me the ZSC now here. Load is shorted now here. That means ZL value 0. The ZL value also 0 here. Then what I will get now here? ZSC. So this is what I will get here? Yes, Z naught into tan h gamma x, Z naught into tan h gamma x. Isn't it, Akshay? This is only h now, not a heck. We didn't convert the lossless line. This is the general case only we are seeing here till now. Next, let us say the load is open circuit line, open circuit transmission line means what? Load is open circuited. This is my transmission line and the load is open circuit means what I can say here? The load impedance, that is ZL value, how much it is, tends to infinity now. Load impedance ZL value tends to infinity when it is open circuited. This characteristic impedance is something Z naught. Now the impedance, the open circuited impedance, I am calling it as a ZOC. ZOC. Now tell me ZOC now. ZOC. That means here the ZL value tends to infinity. ZL value open circuit means ZL value tends to infinity. Yeah. So here if I replace the directly infinite by infinite form, undefined form, so we'll go for El Hospital rule. We'll go for El Hospital rule. Isn't it, Akshay? Hope you all of you know this thing about the concept of El Hospital rule. In the limits we use now, so many times you might use it. Right. So what I should do, I will do the El Hospital rule, and we need to differentiate with respect to what? Here, whichever is the reason for undefined form, with respect to that, we need to do the derivative, the denominator and as well as numerator. Now here, which is the reason for the undefined form? ZL is a reason for the undefined form. So we need to differentiate with what? ZL we need to differentiate. Tell me if I differentiate with ZL now, what I will get now here? This is Z0 into what? Differentiate with ZL now, this is 1 plus this is 0, isn't Akshay? So there is no ZL term now, 0, yes, by what? 0 plus what? Tan H gamma x, isn't it? So from this what I will get now? ZOC, which is equal to what I can write now here? Z0 into cot H gamma x. This is my ZOC and this is my ZSC, the short circuit impedance and open circuit impedance. Now I will see this thing. If I multiply these two, ZSC and ZOC, you will see this thing. What I will get now here? ZSC into ZOC. What I will get now here? This is Z0 square, isn't it? So from this, what I can say now here? Z0. Sorry. So from this, what I can say? Z0, which is equal to what I can say? The square root of ZSC into ZOC. Isn't it, Akshay? Isn't it, all of you? Z0 is equal to square root of what now? ZSC into ZOC. What is it? Z0 is the characteristic impedance, and ZSC, what is ZSC is the short circuit impedance. ZOC is the open circuit impedance. So from this, what I can say now? The characteristic impedance of a transmission line is what? Geometric mean of short circuit and open circuit impedances. The characteristic impedance of a transmission line is the geometric mean of short circuit and open circuit impedance. Right. And we have seen this thing for in case of a open circuit short circuit. Now we'll talk about the, now let us say we'll talk about the matched line, I can say. Matched line. Matched transmission line. Matched line means matched transmission line. The matched transmission line means what it is. Here this is my transmission line, we have like this, and this characteristic impedance is Z0, and here this having some load impedance. The load impedance is a ZL. Load impedance is a ZL. If the load impedance if the load impedance is equal to characteristic impedance. If the load impedance is equal to characteristic impedance, then the transmission line is called as a matched transmission line. So if the load impedance is equal to characteristic impedance, which is called as a matched condition, this is called as a matched condition. This is called as a matched condition. If this condition satisfies, then the transmission line is called as a matched transmission line. If the load impedance is equal to characteristic impedance, then the transmission line is called as what? Matched transmission line. Now I want to find the impedance for in case of a matched transmission line. Matched transmission line. Now we'll see this thing here, this one. Now this is the impedance of a transmission line. We got this thing, that is what? Z of x, which is equal to what? Z naught into ZL plus what? Z naught into tan h gamma x by Z naught plus ZL into tan h gamma x. This is the impedance. Right. Now what I am doing is for in case of a matched transmission line, I want to find the impedance. The matched transmission line means the load must be equal to how much? Characteristic impedance only. Load must be equal to characteristic impedance only. Now if the load is equal to characteristic impedance, now tell me Z of x. Now here in this case, what happened to Z of x? So the load, that is what I can say, this is Z naught into ZL is same as Z naught only now. This is Z naught plus Z naught into tan h gamma x by what? Z naught plus Z naught into tan h gamma x, I can say, isn't it? So now tell me Z of x. Now here how much it is? Z naught. Z of x is what it is? Z naught. Means what happens now here? If the load impedance is equal to characteristic impedance, what happens now here? So where x is the distance, now we can change this x value. This is x is equal to 0, and here this is x is equal to L now. X may be 2 value. X value we can change x value 2. How much the impedance? Z naught. 0, x is equal to 0. Z naught. X equal to 10 meters. How much? Z naught. 100 meters. Anywhere it is, how much the impedance is? Z naught only now. That means what we can say now, under this matched condition, what happens now? The impedance at any point inside the transmission line is what? Same as what? Characteristic impedance. Under this matched condition, the impedance at any point inside the transmission line is same as what? Its characteristic impedance only. That means what I can say here, let us say this is the transmission line here, like this, if we call here. Now this is a load impedance. The load impedance, this is the ZL, which is equal to Z naught, and here this is x is equal to 0, and here this is x is equal to L. Now yes, now the characteristic Z naught here. Now what is the impedance at this location? Z naught only. Impedance at this location is how much? Z naught only. At any way, this is how much the impedance is in Z naught only now. So what happens now under matched condition? Under matched condition means what? When the load impedance is equal to characteristic impedance only under this condition, what happens now here? The impedance at any point is same as its characteristic impedance only. So at any value we can x value 2 meters, 10 meters, 100 meters at any location. Here this is z naught at this point. Here this is also z naught. This point also z naught. This point also z naught. At every point is how much? Z naught only. That's a beauty in these cases. Under matched condition, the impedance at any point is same as its characteristic impedance only. Got it? So what I can say here, write down this point, very important. Under matched condition, under matched condition, the impedance at any point is same as its characteristic impedance. Under matched condition, the impedance at any point is same as its characteristic impedance. Right, got it. Now let's see this thing. Now we have seen the impedance for in case of a general case. We have seen z of x, which is equal to what? Z naught into what? ZL plus Z naught into tan h gamma x by what? Z naught plus ZL into tan h gamma x, isn't it? This is the impedance. Now previously we have seen the short circuited line, lossless open circuited line, and the matched line. Now we'll talk about the lossless line. For lossless line means what? For in case of a lossless transmission line, what happens? For in case of lossless transmission line, what happens? We are going to see now here. For this lossless transmission line, what the condition is a gamma propagation constant, which is a alpha plus j beta. For this lossless line, how much is alpha value? 0. That means gamma is what now? Simply j beta. Gamma is simply j beta only. So from this, can I get my z of x now here? So the z of x, which is given as what I can say, z naught into zl plus what now here? Z naught into tan h what? J beta x by z naught plus zl into tan h j beta x, isn't it? So we can see this thing here, tan h I theta. Tan h I theta is equal to what? I tan theta. Tan h I theta equal to what? I tan theta. Now tell me what I can say this z of x now here, which is equal to what now here, z naught into tell me what I will get here. This is my ZL plus tan h j beta x now. Tan h j beta x will becomes what I can say here, that is j tan beta x I can write, isn't it? By what? Z naught plus j, sorry, one second here, this coefficient is also there now, z naught, j z naught tan beta x. Here this is what, j zl what, tan beta x, this thing, isn't it? This is my z of x here. So this is the z of x. This is for what it is, a lossless lines only. For the lossless line only this formula is valid. For lossy line this formula is not valid. Yes, for lossy line this formula, this is the general formula, and this formula is only for the lossless only. Now here also we'll talk about the short circuit transmission line. I can say this as what now, ZSC. Tell me ZSC, what I can say. ZL value 0. We have seen a ZSC means load impedance is equal to 0. Yeah, simplify, see what you will get. J Z naught into what I can say, tan beta x. What the x is, the distance from way to way, load to source. Now similarly I want to get the ZOC. ZOC, what is ZOC is the open circuited line. Tell me now, here we have seen an open circuited line means, so ZL value tends to infinity. ZL value tends to infinity means what? We need to differentiate this thing with respect to ZL na. If I differentiate this thing, this is 1 and this is 0, this is 0, here we'll get j tan beta x na. That I can write it as what now here, minus j z naught into what I can write now, cot beta x, isn't it? Cot beta x I can say. Right, now if I see the relation between these two, what I can say now here, this is ZSC into ZOC, which is nothing but what, Z naught square. So from this Z naught, which is given as what, ZSC into ZOC. Z naught is given as square root of what, ZSC into ZOC. So the characteristic impedance of a transmission line is what, geometric mean of open circuit, short circuit, like the same relation we have seen earlier also. The relation what we have seen, this relation is valid for lossy as well as lossless lines also, same relation. This is the characteristic impedance. Got it now? We have seen for ZSC, ZOC for matched line. Tell me for matched line what I can say. For matched line, what I can say now here. Yes, Z of x. Matched line means what? ZL is equal to Z naught. Then it will becomes how much Z naught, isn't it? You can see. So this is the analysis about the complete impedance analysis for in case of a transmission lines. Very, very important topic, this one. Very, very important topic.